We are now on to chapter 5, which is all about forces and friction. So this first section is just about resolving forces. So if I've got here, it's just a book on a table and it's being pulled with a force of F up here at this angle. Now I can actually resolve that force into two components. We've got the horizontal component, which is pulling the book in that direction of motion along the table. But there's also going to be a vertical component of that force. So if you think about that, force can be made up of the horizontal and the vertical, which makes that triangle there. And obviously, if I wanted to find the horizontal component, it would be F and then cos theta. That angle there would give me the horizontal component. The vertical component would be F sine theta, or if I could work out the angle to the vertical, then it would be F cos whatever that angle was. So let's have a look at these questions. So I've got these different forces acting. So here's 9 newtons acting at an angle of 40 degrees to the horizontal. And it wants me to find the component of the force in the X direction, in the Y direction, and then write it in the form something I plus something J, where I and J are the unit vectors. And we talked about this when we did those last year. So I is the unit vector in the X direction and J is the unit vector in the Y direction. So I've got this force of 9 newtons acting, and it's acting at an angle of 40 degrees to the horizontal. Well, I think it's quite easy to see what the component's going to be in the X direction. I'm just resolving that force into the horizontal. So in the X direction, I've got an angle of 40, so it's going to be the component, how do I spell component, in the X direction. Well, it'll be 9 cos 40. And that is equal to, I think we should get 6.89. Let's check. 9 cos 40, 6.89 newtons. So that's the component of the force in the X direction. Now, the component in the Y direction will be, well, we could say I'm going to do it as 9 sine 40 because I can see that that would give me the vertical component. You could think, well, I know that that angle there will be 50 degrees. So you could do it as 9 cos 50 if that's easier for you. I think 9 sine 40 is easy to see as well. So 9 sine 40. And that will give me, let's have a look, 5.79 newtons. So I found the component of the force in the X direction and in the Y direction. So if I'm writing it using the I and J vectors, then I can say that it is 6.89 I plus 5.79 J. And that's written it using the I and J vectors. That is my force. Okay, let's go on to this second one then. I've got 100 newtons acting down here at an angle of 18 degrees to the vertical. And there's loads of different ways of doing these questions. What I'm going to do is, if when I'm working out in the X direction component, so I'm looking for the component in the X direction, well, I can see that the force would be going here in the negative X direction, which would be 100 sine 18 that way. So therefore, the component in the positive X direction is just negative 100 sine 18. Now, there's loads of different ways of doing it. You could say that it's 100 cos and then work out that whole angle. I think this way is easy for me, but you'll get the same answer if you've done it in a different logical way. So minus 100 sine 18. Oh, not tan, sine. Gives me minus 30.9 newtons. So I'm saying the component in that direction is minus 30.9, and that makes sense. Obviously, I'm expecting it to be negative because I know the force really is going that way. It's going in the negative x direction. So minus 30.9 in the x direction. Then in the y direction, now I can see the force is going downwards, so it's going in the negative y direction. So it's going to be 100 cos 18 downwards, which means that in the positive y direction, that will be negative 100 cos 18. So I've just resolved it in the negative y and made it negative. So negative 100 cos 18 is equal to minus 95.1 newtons. And then the final section, writing that in terms of I and j, well, that would just be minus 30.9 I minus 95.1 j. And just check back to your diagram, that's what you expect. It's going to be negative in the I direction and negative in the j direction. Okay, next question then. It's similar to that idea of a book on the table. So we've got this box of a mass 8 kilograms on a smooth horizontal floor. Remember, smooth means there's no friction acting, so we don't need to worry about friction here. A force of 10 newtons is applied at an angle of 30 degrees, causing the box to accelerate horizontally along the floor. So I can think the acceleration is going in this direction. The box is going across here. That's my acceleration. Work out the acceleration of the box and calculate the normal reaction between the box and the floor. So if I think about first what forces I'm going to have acting, I've got do this in green. I've got the weight of the box coming down, which is 8g. And I've also got the reaction between the box and the floor going upwards. And then my final force is this 10 newtons. Now, I can split the 10 newtons into a vertical and a horizontal component, and that's going to really help me out. For the first part of the question, I'm going to need the horizontal component. Because remember, we've got to use Newton's second law, which is F equals ma. So if I'm working out the acceleration, I need to know the force that is going in that direction, in the acceleration direction. So my force here will be 10 cos 30. That's the force pulling in the horizontal direction. 10 cos 30 is equal to the mass of the box, which is 8, times the acceleration, which is what I'm trying to find. So a bit of rearranging. I can find out that the acceleration is going to be 10 cos 30 divided by 8. So 5 root 3 over 8, that's going to be 1.08 meters per second squared. There's my acceleration of the box. Now, part B is looking for this normal reaction. Well, I know the box isn't accelerating vertically, it's only accelerating horizontally. So vertically, all these forces are balanced. So the 8g downwards is equal to the reaction upwards plus the upwards force caused from the component of this 10 newtons. So if I split that 10 newtons, we've already found the horizontal component, that was 10 cos 30, and vertically it will be 10 sine 30, acting upwards. So I've got 8g downwards, r and 10 sine 30 upwards, and they'll be balanced. So I can rearrange that to find the reaction force, which will be equal to 8g minus 10 sine 30. So I've got 8 times 9.8 minus 10 sine 30. and I get 73.4 newtons. So the first part, I used Newton's second law, F equals ma, where we're using the force in the same direction as the acceleration. So I wouldn't just use that force 10, because part of the force is going upwards, which is not useful to me. I'm just using the horizontal component in the same direction as the acceleration. Then for the second part, sorry about that. Second part, I'm using vertical equilibrium. So any of those forces down equal to any of those forces up. Let me just balance that. There we go. Okay, so next we're going to use the triangle law of vector addition, which will find the resultant of two forces. We kind of looked at this when you do vectors at GCSE. You say if you've got a vector A and you've also got a vector B, then the resultant vector, when you add them both together, is just A plus B, which goes from here all the way to the end of B. So the same sort of idea is here. We've got a force P and a force Q acting on this particle. And we want to know the magnitude and direction of the resultant force. Well, if I just put force Q and then stuck force P on the end of it, the resultant force would be the force that takes me from the start to the end. So I can draw that as a picture if I want to. So we've got, there's force Q coming down. If I think about this, is going to be 30 degrees. And also Q is magnitude 8, so size 8. And then I put force P on the end of that, going up here somewhere. What can I fill in then? I've got, well, I know that P acts at an angle of 45 there, and it's got a size of 10 newtons, so that's 10. I can probably then work out what this angle here is. I'm going to have, well, that bit there is 45. That bit there would be 60 because it makes up the other 30. So that's 105 degrees, that angle there. And the resultant force, which is what I'm trying to find, is just this one that goes from the start to the end. That's my resultant force. And I want to know the size of it and the direction, the magnitude and the direction. What we've got here, though, is just a nice triangle, and I can use my trigonometry laws to work out what R is going to be. So to work out the magnitude of R, I can use the cosine rule. So you might need to remind yourself of the cosine rule, but it's that A squared equals B squared plus C squared minus 2BC cos A. So in other words, R squared is equal to 8 squared plus 10 squared, these two sides, minus 2 times 8 times 10 times cos of that angle 105. And I can solve that then. I can work out what R is going to be. So I get R is the square root of all that. Let's do that in one go. 8 squared plus 10 squared minus 2 times 8 times 10 times cos of 105. Close that bracket. R is 14.3 newtons. That's the magnitude of the resultant force R. And I also want to know the direction of R. So I want to know what this angle is here that R is acting at to the horizontal. And for that, I can use the sine rule. So I know that R, which is 14.3, over sine of 105, could have done this the other way around, is equal to, what should we say, 10 over sine of, well, theta plus 30. And with a bit of rearranging, you can work out what R is there. So I think in the end, you get that theta plus 30 is equal to 42.3, or 37, in fact. and therefore theta will be equal to 12.4 degrees to 3 significant figures. So to summarise then, at the end, I can say the resultant force has a magnitude of 14.3 newtons, that's what we worked out first, and a direction or acts at an angle of 12.4 degrees to the horizontal. So I found the magnitude and I found the direction of the force. And that was using my cosine rule and sine rule using vector addition.